Okay, we start with this. We have a region, the yellow region here, where we have a uniform electrical field, meaning the electrical field in that region is constant throughout the region. It's a constant electrical field throughout the region. And here they show us that the electric field is actually pointing towards the right-hand side of the screen. Now, the question is, in what direction does the force on a negative charge at point A? This is saying, what if I have a negative charge here? What would be the direction of the force, the electrical force acting on it due to this electrical field? What we need to do is remember that the force due to an electrical field is given by this expression. F is equal to QE, where Q is the charge and E is the electrical field. Now, if my Q is positive, then the force has the same direction as the electrical field. If Q is negative, then we are multiplying E by a negative number, meaning that the direction of the force then is opposite to the direction of the electrical field. Here, I'm going to try to draw it in two different colors. The electrical field, I'm going to draw it in red at the position where we have A is pointing in this direction. Now, the force is opposite in direction to E because, as we mentioned, the charge is negative. So the direction of the force, it's going to be this way. So it is to the left. Now, in this question, they tell us when a negative charge is moved from A to C, the electric field does what kind of force? Positive work. What kind of work? Positive work, zero work, or negative work? Now, we mentioned a few minutes ago that the electrical force is pointing in this direction. My displacement in this case from A to C is in this direction. Remember, work is Fd cosine theta. Our F here is F due to the electrical field. Our D is the displacement from A to C. And the angle between them is 90 degrees in this case. Cosine of 90 degrees being 0, that tells us that our work is 0. So that's our answer. Okay, in this question here, when a negative charge is moved from A to B, what can we say about the work? Okay, doing the same analysis. This is the direction of our force. This is the direction of our displacement in this case. Now, again, the work is Fd cosine of theta. F is the force due to the electrical field. D is the displacement. Now, cosine of theta is cosine of 180 degrees because that's the angle between D and Fe. So it's going to be minus Fed, which tells us that we have a negative work. Okay, in this question here, we are being asked, what if a negative charge is moved from A to B? What happens to the electrical potential energy of the charge? Okay, so what we just found out from the previous question is that the work due to the electrical force is negative work. If the work is negative, the work due to the electrical force is negative. Now, the potential energy due to that electrical force is going to be the negative of the work due to the electrical force. That's the definition of the change in potential energy. So since we ended up having a negative work, and we are getting the negative of that negative work, the change in electrical potential energy must be positive. Then we can say that the electrical potential energy increases. In this question, we don't have a uniform or constant electrical field. Our electrical field is going to be due to this positive charge. And what we know about the electrical field due to a positive charge is it is given by this expression in magnitude, kq over r squared, and the direction for a positive charge is going to be radially pointing away from that positive charge. So if I'm going to use, let's say, a blue color pen to draw the direction of the electric field, I'm going to draw it radially outwards here, radially outwards here, a smaller one here, and so on. Okay, now the force, the electrical force, since we still have a negative charge, is going to be opposite in direction to the electrical field. So in here it's going to point this way, that's my electrical force. Here it's going to point this way. Here it's going to point this way. Now, so to determine if the potential energy is going to increase or decrease, we are going to analyze the problem like we analyzed the other questions. What's the sign of the work done by the electrical force? Okay, now our displacement is going to be from A to B. This is my displacement. And the work done by the force F is going to be F times the displacement times cosine of theta. However, from what we know about conservative forces is that the work done by a force does not depend on the path taken. That's one key component about, one key fact about conservative forces. Meaning we can go straight like we drew it this way, or we can take a different path. For example, here I'm going to take a simpler path to help me understand conceptually what's happening in terms of the work. What I'm going to do, I'm going to move the charge along this arc here so that the force is always perpendicular to the displacement when I go from A to C. And then once I reach C, I'm going to move the charge along the radius till I get to point B. So in that case, the work due to the force F is going to be equal to the work moving the charge from A to C plus the work moving the charge from C to B. The work moving the charge from A to C is going to be 0. It's going to be 0 because F is along the radius, so the whole time I'm moving the charge along that arc, the force is perpendicular to the displacement. So it does not do any work. My theta is equal to 0. Now, the work to move the charge from C to B, the force is opposite in direction to the displacement, so that means that the work is negative. So the work due to my electrical force is negative. The change in potential energy due to that electrical force is the negative of the work done by that force. Since my work is negative, that means my change is positive. That means my electrical potential energy increases.